started now. Everything is working. So this week you guys covered using Newton's law, so we're going to go over some particular use cases for it. I'm going to go over things like the spring force. You have kinetic friction, rolling friction, right? Static friction as well. We'll go over some of those concepts, reinforce some of those things, and then we can do some quick practice problems that can help prepare you for the quiz. So first of all, right, first force that we can kind of talk about, because you guys talked about things like the normal force, for example. I don't know if it was last week or earlier this week as well, but it's a very common concept, the normal force. But before I kind of go into spring forces, which is the next type of force that we're going to talk about, do you guys fully understand what the normal force is? Not quite. So normal force isn't necessarily going to be equal to mg, right? So that's where I think a lack of examples in some of these lectures is going to throw some people off. And I can go over more specifically what the normal force is. It's a very common concept that people kind of get wrong. So the normal force, we can define that as a contact surface force, right? So it's a force that will give solidity, quote unquote, to an object or to a surface specifically, right? So we can think about the normal force as the force that kind of prevents an object from sinking through the floor or going through a wall, for example. It's what gives the wall or the floor its solidity. And what that means is, right, is if I have a floor like this, right, this floor right here, and I'm standing on top of this floor, right? Well, I will be kind of exerting some kind of weight, right, downwards like this because of my mass, right? And we know that mass times your acceleration due to gravity, mg right there, absolutely, should be your force of gravity. Now, in this specific use case, right, in this specific situation, if this was the only force that was acting on the person, then what would happen to them if this was the only force that was acting? I'm asking, by the way, like that's how I can like engage with you guys as well, so we can kind of all just kind of talk about it. Yeah, exactly. So if this is the only force that's acting on the person right here, and there's nothing kind of acting back on the person, then the person would simply sink through the floor, right? Same thing like if you look at if you're resting your hand on a wall or something like that, if you're leaning on someone, well, that person will have a certain surface of contact between you and that other person, or if you're leaning your hand on a wall, then there's a surface of contact, obviously that wall between your hand and the wall, right? And so what's going on is that you are exerting a certain force, and then that surface, right, is exerting a force opposite and equal to yours, right? And so that's what gives the surface some sense of solidity, that gives it a sense of a solid object, right, or a solid surface. Because otherwise, for example, if you were to lean, right, on like a cardboard, like, I don't know, poster or something, you could very well like just topple over, right? Because maybe the normal force isn't as strong between you and that, cardboard poster thing, right? But um, that's the idea kind of a normal force, is that it's a force that gives an object, gives the surface some solidity, right? And so in this case, normal force is going to be pointing directly upwards. Well, you might think in this specific use case, it is simply just equal to mg. Well, in this case, it is. Actually, give me 1 second. Got to interrupt real quick. Someone has joined in the Blackboard Collaborate page, so I'll let them know that it'll be in the Discord. Okay, so just let them know there, my bad. Yeah, so for normal force, right, in this specific use case, you have it where it's going to be directly equal to your force of gravity, right? So it should cancel it out completely to where that this person is standing stable, not sinking through the floor whatsoever, right? So in this case, Fn equals mg. But you might also have, you might be leaning, right? Or you might have like your hand acting a force this way on the wall. And in that case, right, this might be your force of hand on the wall, right? Well, if you're this person right here and you're extending your hand this way, right, your force of gravity is going to be down here. Let's say this is a floor and here's the wall, right? Well, then how does force of gravity relate to the normal force in any sort of way here? It doesn't really, right? Because force of gravity would just be, the earth acting on you, right? Um, Giving you some weight, right, due to the gravitational force, right? But if we're just looking at this surface of contact right here between your hand and the wall, well, your hand doesn't necessarily like encompass your entire force of gravity, your entire weight. So your hand will be exerting a force on the wall, right? But then the wall will be exerting an equal and opposite force to the left, and we call that the normal force, right? So the normal force is any type of force that's going to be giving a surface of contact solidity and acting opposite to another force to, once again, like I said, give an object solidity, and prevent like sinking through the floor or just going through a wall, basically, right? And the idea here is that we can say that this normal force is going to always act perpendicular to the surface of contact. So if your surface of contact, right, is the floor where it's going along the x-axis, left and right, then your normal force has to be at a 90-degree angle, right? A 90-degree angle to the surface of contact. If it's a wall where it's straight up and down, then it's at a 90-degree angle, right? Either left or right. And you can determine if it points like this way or this way, both at a 90-degree angle. You can determine if it points up or down or left or right based on what's acting on it, right? So if your hand is pushing to the right, then it would only make sense based on the idea of a normal force giving an object solidity. Does it make sense for the normal force to be pointing in the same direction? No, exactly, right? And the reason why is that then you would have a net force pretty much to the right, and that would mean basically you're leaning on it, and then you topple over, right? And if we're going once again by that definition that the normal force should give a surface solidity, right, then it should be the opposite direction to where, okay, if I'm exerting 20 newtons by leaning on this wall, then this wall will exert a negative 20 newtons, right? So an equal magnitude, opposite direction force, right? To where that there's a net force of 0 and I can just freely just kind of lean on the wall there without any issues. Same thing with if you're just standing on the floor, right? If I'm 100 newtons, right, downwards, that would be technically negative 100 newtons because it's along the negative y-axis, right? Then the floor would exert a positive 100 newton normal force, right, to prevent me from sinking through the floor. Otherwise, if your gravity is bigger, then you'll start sinking. That's the idea of a normal force there. So it's not necessarily always equal to mg because, like I said, like if we're interested in this wall right here, right? Well, it'll be your hand, and wherever the wall exerts back on your hand. Your gravity would be over here, but pretty much to the left, right? It shouldn't have any kind of correlation to the gravity whatsoever. Now, an example that we'll kind of be going through, and you might have already seen in your lecture, right, is an inclined plane, right? So you might have like a block or something that's being moved up and down an inclined plane, right? So you might have this block kind of sliding down right here, right? Well, the idea is that the gravitational force, you know that it's always pointing downwards, right? Directly downwards. So your gravitational force, your Fg, will point directly downwards like this, right? But if we're going by the concept once again that the normal force is a force that is perpendicular, forming a right angle with the surface of contact, right? Let me ask this first. What is the surface of contact here? What's our surface? Exactly, surface is the inclined plane, right? So if this is our surface of contact, right, and the normal force should be at a perpendicular angle to the surface of contact, then how should the normal force be pointing? In what direction should it be pointing to? It didn't kind of like give me you don't have to say really specifically, but you can kind of say just roughly or generally what direction it's pointing in. So up, you mean up directly like this? Or like this, or like this, or like this, or what's going on? In the direction of the box, so kind of like up and to the left almost, right? Is that what you guys are going for? Cool. Yeah, so that's absolutely right. And the reason why is then if it's pointing this way, right, here's our surface of contact, here's the force, there's the right angle, right? So that's our normal force right there on an inclined plane. Because otherwise, right, if there is no normal force, then this block would simply just sink through. Well, you might be thinking, well, the force of gravity just acts simply just downwards like that, right? And the normal force is acting upwards along a different direction. Well, then, what's down here, right? To prevent it from sinking through. It doesn't make any sense, right? Well, the idea here is that your force of gravity is going to have both x and y components, right? So you might have, this would be your FGY. This would be the y component of your force of gravity. And this would be your x component of the force of gravity. In which case, this normal force in the tilted y direction is going to be equal to the force of gravity in the y direction, the y component of the force of gravity, right? Equal and opposite. So this might be 100 newtons upwards like this. This might be a negative 100 newtons, right? FGY, whatever you get for it, is not the value that you will refer to force of gravity as, right? So you can't just say force of gravity is also a negative 100 newtons, right? FGY is only a negative 100 newtons. That's just a component of force of gravity. You would also need FGX, right? And then you can use Pythagorean theorem to figure out what FG is. So if you had like FGY is 10, FGX is 10, then 10 squared plus 10 squared, right? A squared plus B squared equals C squared, in which FG is your C, basically your hypotenuse, right? So it'd be saying like 100 plus 100, right? That's 200, and then the square root of 200 is going to give you your FG, right? That's how you can get your FG, for example. So this is kind of going further into the lecture right here, and I'll go over that again a little bit later, but I just want to kind of reinforce what the normal force is before we kind of moved on, right? Because I know it's a kind of a confusing force for some people, and it's just I want to clear up any misconceptions on that, because I know in most of your examples it's going to be equal to FG in the sense that it's usually just a straight up and down, right, direction, right? You might have like a block sliding on a floor, and if we're looking at a floor, right, since the floor is horizontal like this, you have a block or something that you're pulling or whatever you're pushing, the normal force points directly up and down, perpendicular to the contact surface at a 90-degree angle, and there's your gravity pointing downwards as well. So those are the most common examples, but in situations like these is where things get a little tricky, right? And that's why you have to know that it's not just Fn equals mg, it's Fn opposes any forces that would be acting in the direction of the, I guess, acting on the surface of contact, basically. So it gives, like I said, the surface of contact solidity, gives the surface some solidity, gives this inclined plane some solidity right here. That way, the FGY doesn't overwhelm everything and just sink through. Allows the box to sink through, right? So Fn will oppose FGY. That way, this object can simply, because if these two are Fn and FGY, if they are equal to each other in magnitude, opposite in direction, like this is 100, this is negative 100, they cancel out, then really the only motion that you should observe when you allow a block to kind of slide down here is just along the surface of the inclined plane, right? So it should just go downwards like this to the left, and that's the x component of gravity. Does that make sense for everyone? everyone else on the same page as well? Awesome. Let me go ahead and erase this real quick. Alrighty. So now we can kind of move on to this week's lecture stuff, right? So we have spring forces. So for the spring force, right, generally I'll define this similarly kind of to the normal force in the sense that you want to kind of generalize and understand what the spring force is as a whole, right? So the spring force, we refer to that as a restoring force. It's a force that restores an object, right, to its original position. And in this case, when we're looking at spring forces, we're obviously looking at springs, right? So if you were to ever just kind of grab a spring like this, right, push it in, you want to compress it, right? Well, if you let go, what direction should that spring go back into, essentially? Should it stay compressed, or it goes to equilibrium, right? And what direction would equilibrium be? If the string was originally right here and then you compressed it this way, right, then it would just pop back to the left, right? It would just pop back to the left. Now, if I were to pull it this way, then it should do what? Should it stay to the left, or what's it going to do? It's going to go right, exactly, right? And so what you can see here, roughly, is that that reinforces the idea that it's a restoring force. It restores an object to its original position. In this case, it restores the spring to its original position. So if the uncompressed, unstretched length and the look of the spring is like this, if we compress it, it's going to want to go back and revert to this original state. So the spring force is to the left, despite me compressing it to the right. So essentially, it tries to reverse any action or any force that you impart on it, right? So if I'm compressing to the right, the spring force as a restoring force is going to want to stretch it back to the left. If I stretch it to the left, it's going to want to restore it, compress it again back to the right. And so with all springs, right, like we said, we have an equilibrium length, an original length. That's its original state. That's equilibrium state. That's where it's at rest, pretty much, right? Without you stretching it or without you compressing it. If you were to push or pull on it, right, like we did here in these examples, then we're going to change the equilibrium length of the string by a certain amount, delta L. So delta L, whenever you see that delta symbol, right, it just means that there is some final state or final length minus some initial length or initial state, right? So delta L would be, for example, like if we started at an equilibrium length of 6 centimeters, and then all of a sudden when we compressed it, it's now at a length of 3 centimeters, then your delta L would be 3 centimeters minus 6 centimeters, and that gives you a delta L of negative 3, right? So, and you can see here in a sec, I'll kind of explain this real quick. So with the equation now of the spring force, right? This is actually a little bit incorrect in the sense that it doesn't quite show or portray accurately the idea of the spring force being a restoring force. So really, what the equation should be is a negative K delta L, right? Where this is going to be the magnitude here as well, right? So, actually, no, my bad. So, I think I actually threw things off a bit by looking at the equilibrium length and stuff. My bad. So, what you should refer to it as, so what you should refer to the equilibrium length as, your equilibrium length is always just at x equals 0, right? Let's just call that as your original length, right? That's your equilibrium length. It's always going to be x equals 0. That's what I messed up there. I was trying to just explain what delta L was, but I forgot the most important rule for a spring is that you always start at an x equals 0. And so if you're going to the right along the positive x-axis, right, then essentially what you're doing, you're going from this initial state and maybe to this more compressed state to the right, maybe positive 3 centimeters to the right, right? And so in that case, if you do your delta L, LF minus LI, right, then you have a change in the length to the right of 3 centimeters, right? Now, still, like I said, the equation is wrong. It's just, and I'll explain why here. It's because the equation should be negative k x or negative k delta L, right? So why is it a negative sign there in the beginning and not just a positive like they have it in the lecture slides? Well, the idea here is that once again it refers to the spring force being a restoring force. If my delta L was a positive in the sense that I stretch it, or I compress it, my bad, from an equilibrium length of x equals 0, the starting point, to the right along the positive x-axis, 3 centimeters like this, where I compress it 3 centimeters, to where my final state is at 3, and my initial is at 0, right? So that gives me a delta L of 3 centimeters. Well, I plug in delta L is 3, positive 3, right? And my K, my spring constant, is always going to be positive no matter what. Well, that gives me a spring force that's negative, let's say 30 newtons, for example, right? That makes sense in the grand scheme of things of the spring force being a restoring force. Why? Because if I compressed it to the right along the positive x-axis, giving it a positive displacement, then I should see that my spring force should be a negative force in the opposite direction to the left along the negative x-axis, to where it restores it to its original position. If I were to just use this equation right here, right, what happens is, if I were to, remember these are absolute value symbols, right? So if this was delta L positive, right, and the K is positive, then what you get is simply just a positive spring force, and that doesn't match, right? So I prefer to where it's this F equals negative K delta L, that way you can get the actual direction of the spring force. Here they correct it by giving you the absolute value on the left-hand side as well, which makes sense in the fact that the absolute value always makes anything negative positive, right? Sure, that makes sense, but that's not very helpful, because what you're going for is you're trying to figure out what the spring force is, right? And I just prefer to have this equation going on here where it's F equals negative K delta L, because it actually gives you the direction of the force, of the spring force, right? Now, if we did the same thing here, if we pulled it to the left, a negative x distance or displacement, right? We had 0 centimeters as our equilibrium position, and then we pulled it to the left, let's say another 3 centimeters, but to the left, negative 3 centimeters, right? Well, then your final state is at negative 3, and your initial was at 0, LF minus LI, right? So your delta L is negative 3 centimeters. If you were to plug it in here, delta L is negative, negative 3, and this negative, everything becomes a positive. And that makes sense once again, because if I'm pulling to the left, it's going to want to restore to the right. It restores it to its original position, right? So that's the concept of the spring force here being a restoring force. It always points back towards the equilibrium position. Now the K here is the spring constant, and that's unique to every spring. Every spring, that's basically like going to be an indication of the stiffness of a spring. So if you have a really big spring constant, big K, it means you have a stiff spring. If you have a really small K, small spring constant, it means it's a loose spring, right? And this equation, overall, we know that as Hooke's law. Does that make sense so far for spring forces? Awesome. So here's like a little quick check just to help you guys kind of visualize what's going on with the spring constant as being a measurement of stiffness, right? So it says the restoring force of the 3 springs, which is the spring force, is measured as they are stretched. Which spring has the largest spring constant? Well, if we're looking at spring constant, right, we have FSP is equal to K, negative K delta L, right? Now, if equation like this, you can kind of think about, well, what is this equation kind of modeled on, right? From a general algebra standpoint, right? From a general algebra standpoint, if you have a line that looks like this, just a linear line like that, what do we know from algebra should be the equation for that line? What format should it be in? Like if I were just to make up an equation for this, it should have a general kind of format. Yep, exactly. Y equals mx plus b. For any linear line like that, your formula is going to be y equals mx plus b. Well, if it is y equals mx plus b, right, we have FSP is equal to k delta L, where k is a specific constant, right? The spring constant. We can see really quickly that things kind of match up with the linear equation right here, right? So y equals mx plus b, y is kind of your spring force, k is kind of like your slope, delta L is basically like our variable right here that we're changing, which is the displacement of the spring. So that's kind of our x, and then our b, which is kind of be 0. And that's our y-intercept, right? Which makes sense because everything starts here at 0, right? So that's fine. Now, if k, based on this kind of relationship, we're assuming that to be the slope, right? Then what should that mean, right? If they're asking us which has the largest spring constant, then we're looking for which one has the largest slope. So for your slope, having a larger slope means that you're going to have a steeper line or a steeper curve. And for a smaller slope, you should have a shallower line or a shallower curve. So A has the steepest curve, right? And C has the shallowest curve or shallowest line, right? So this would have the smallest slope and this would have the largest slope. Does that make sense? Awesome. So there's another example here as well that will just kind of be more specific to how you can calculate spring force and stuff like that. So you have a 15 centimeter long spring, and it's at equilibrium length. It's attached to a wall, and then when you pull it horizontally with a force of 0.10 kilonewtons, the spring stretches to a length of 17 centimeters, right? What is the value of the spring constant? Well, if 15 was the equilibrium length, right, and now we're stretching it to the length of 17, remember we're going by like final and initial state, final initial length, right? If we're assuming that this is our equilibrium length. So 17 minus 15, right? Your delta L is equal to LF minus LI, 17 minus 15. Then we have a displacement of positive 2 centimeters, right? And 2 centimeters, we can convert that to 0.02 meters because we want everything to be in SI units, right? And so we know that the spring force equation is FSP equals your negative K delta L, right? Now, we're not quite sure what orientation this spring is in, right? We're not sure if the spring, like if the wall is this way and the spring is this way, so stretching it means pulling it to the right. Or could it be that the wall is this way and the spring is this way, and so stretching it means pulling it to the left? Because then you would have different values or different signs for your force. Because if you're stretching it to the right like this, then your spring force should be to the left, a negative. And if you're stretching it to the left like this, then your spring force should be positive, right, to the right. They don't give us an indication of what's going on here exactly. So we can just assume then, right, that direction is not going to be a problem, and you can see that also from the answer options here. They're not really worried about the direction. They want to make sure that you have the magnitude right, that you have just generally how like big this force is, basically, right? So that's when you can kind of revert back to this equation where you're looking at just the magnitude, right? We're just looking at absolute values because we're not really quite sure what is going on with this situation, right? We don't know if the wall is to the left and you're stretching it to the right, or if the wall is to the right and you're stretching the spring to the left, right? So what you can do then is set the equation as FSP is equal to K delta L, right? And the should be absolute value of either side here, right? And you have your spring constant, that is the thing that you want to be calculating for, right? So they gave us 0.10 kilonewtons as the force, right? There's our K, and then here is our 0.02 meters, or our 2 centimeters for our delta L. This is kilonewtons, so we can just multiply this by 1,000 if we wanted things in newtons, right? But it looks like our answer options are going to stay in kilonewtons per meter, right? So we definitely had to convert from centimeters to meters first in order to make sure everything is corresponding with the correct units of the answer options. But if they were asking us for newtons per meter, then you would just simply multiply this kilonewtons by 1,000 to get the number of newtons, right? So essentially you would just divide your 0.10 divided by 0.02, and that should give you your, what was I going to say? Your spring constant, right? And so if we do that, 0.10 divided by 0.02, we should simply get 5 as our 5 kilonewtons per meter as our value for the spring constant. Right? Does that make sense so far? But yeah. There's also kind of like specific situations with these springs that you might not just have it where it's just pulling to the right, pulling to the left along a horizontal surface. You might also have the spring kind of in the vertical direction. So you might have like a block hanging by the spring. And so in that case, it's not spring force to the left or spring force to the right. Now it's in the direction of, or opposing the direction of the mass or the weight of the block, right? So if the block is trying to pull it downwards like this, stretching the string downwards like that, right? Then the spring force is going to try to want to restore it back to its original position. That's why, like, if you were to think about it almost, right? If you had a spring hanging from your ceiling, you try to pull it down, right? And then you let it go, well, it'll just kind of shoot back upwards to try and restore it to the original position. Now, if we just have like a block like this hanging on the spring is not moving, mass isn't moving, it's not falling down to the floor or anything like that, well, then you know at that point, whatever spring force is trying to restore the spring to its original position is going to be equal to, but opposite direction, to the gravity, to the weight of the block. That way, there's, obviously there's no net force because the block isn't moving, the spring isn't moving, right? If they're just hanging there static. It's in static equilibrium is what we call it, right? So there's no net force in this point because whatever spring force is acting to restore the spring to its original position, it's being opposed by the force of gravity here, and vice versa, right? So in that case, if you were to, for example, right, since we have some experience writing some net force equations, if you have F net, and we want to write net force for this, right, then FSP is pointing upwards, minus FG pointing downwards, right? In which case, we know that there's no net force because there's no net movement, right? There's no acceleration going on here with the block. So you have your net force is 0, and so your spring force should just equal the magnitude there of your gravitational force. Fk is kinetic friction when Fs is smaller than the force moving it. Yes, excellent. We'll get into that here in a second. So yeah, kinetic friction is a friction that kind of kicks in when the force that is being applied to an object has started to exceed the static friction force. That's your Fs. Now, static friction force, I'll like repeat this and explain it like a million times throughout the semester because it is such a confusing force. And there's so many applications for it, but more or less, and it depends on the situation as well. But just as a beginner kind of explanation for it now, it's basically the friction force that will prevent an object from slipping or sliding, right? So if you have your car parked up on a hill, right, then the static friction force between the tires, right, and the pavement or the road or whatever, right, there's a static friction force that will prevent the sliding and slipping of the tires on the surface, right? And so if, for example, like I said, if the car is parked this way and naturally, because of gravity, right, because gravity is pointing downwards like this, there's, like I said, FGY and FGX components. Well, FGX is going to want to tend to let the car, due to the weight of the car, it's going to want to tend to have it slide down the hill, right? But then we might have a static friction force, right, that will be basically opposing that FGX and trying to make sure that the car stays in its position at static equilibrium and not slip or slide. As soon as an object starts to slip or slide, then that's where we have kinetic friction, right? That's where we have kinetic friction. Kinetic friction, we can think about that as the friction of two, or friction between an object that is sliding and the surface that it's sliding on. So kinetic friction, think about that as sliding, and then static friction is the force that prevents that slipping and sliding. But yeah, and kinetic friction as well. Like, I mean, friction is friction. Like, you under just from a general kind of idea what friction is outside of physics from its formal concept. It's just that a force that will basically oppose something else, right? Um, and in the case of static friction, like I said, it's opposing slipping or sliding. And then for kinetic friction, when you're actually sliding, kinetic friction is basically like just trying to prevent the sliding that's already going on now, right? So like static friction is like, all right, well, let's try and stop this, before it happens, before sliding and slipping happens, let's try and stop it. Once it actually starts happening, kinetic friction is what kicks in. It's like, okay, well, now it's going on. Let's try and just control the situation and stop it now. That's what kinetic friction is kind of doing. There's also rolling friction. We don't really use that too often. I don't think we might have had like one problem ever on a quiz to even think about mentioning it. But really, you're only going to focus on static friction and kinetic friction for this course for the most part. Very rarely do you ever have rolling friction. Rolling friction would just be with wheels, and you might think like, okay, well, tires too, right, for cars and stuff. But we very, very rarely ever factor it into any of our problems. So I honestly wouldn't even worry about rolling friction. But yeah, does that make sense as well for your question about friction? Awesome. I don't want to go over like too many examples because I want to make sure I cover all of the concepts as well. So we can go back if we have time to look at all these, but a lot of them are worked out anyways, and I can share my lecture slides as well with you guys, so you guys have notes on this stuff and you can refer back to it later. I will send a link to the Google Drive and the Discord here and the group meets as well, so you guys have access to that. And I'll drop a link at the end of the session here in the chat, so you guys can have that as well. But yeah, I'll just kind of skip some of these problems because some of them are just like straight up just applications of the equations, plugging things in and stuff like that. Now we can move on to the concept of apparent weight. So obviously we know that Fg is your actual weight of anything, right? So Fg is mg. But there's also a concept called apparent weight, and we define that as just kind of like what you feel. It's what you apparently feel, right? That's kind of how we look at things. So an example might be, right, if you were in an elevator, right, and they love to use elevator problems, and I can kind of show what's going on here. Well, if you're in an elevator and you are moving upwards, right, then you might feel that you're apparently a little bit heavier, right? If you're moving upwards in an elevator, you're going from the first floor to the second, third, fourth, right? You might feel that you're just a little bit heavier, essentially. Now, if you were going down a couple floors, right, you might feel a little bit lighter. Have you guys ever felt that before? Yeah, so the concept of apparent weight here is pretty much looking at how the value of normal force will change in response to a net force, right? And so if we go back to here, the apparent weight, we define that as the magnitude of all supporting contact forces, right? I remember what I said about normal forces. Normal forces are contact forces, right? They're a force between another force, right, and the surface of contact. So if you have a surface of contact like this and you have gravity acting on that surface of contact, then normal force will act to oppose it, right, to make sure that you aren't sinking through the floor. Or if you're resting your hand on a wall, right, then your hand is exerting a force on the wall, and the wall will exert an equal and opposite force back on you to make sure that you're just not, just sinking, or, well, I guess, going through the wall pretty much, right, toppling over. Now, when we get to this idea of apparent weight, it's usually in this context of the elevator kind of example, right? And what it's basically referring to is when you have some kind of net acceleration in one direction or another, and your net force, or your net force has a component that is the normal force or some other contact forces, usually only just normal force, then based on that net force, right, your apparent weight or your apparent normal force might change a little bit, right? In the sense that, here, I'll kind of explain it. So here's your weight, right? You might be weighing 100 newtons. Awesome. That's, if I go on a scale, hop on a scale, right? It'll give me my weight. It'll be in pounds, obviously, but you do some, conversions, all that. You'll get your mass in kilograms, whatever, and then you can figure out what it is in newtons, right? Now, that's your real weight. There's no question about that whatsoever. But the thing is that when you're standing on a scale like that, do you have really any net force? Not really, because what's going on is that if I'm just stepping on a scale like this, if this is my contact surface, I'm stepping on the scale, if I were to write a net force for this, well, there's a normal force between me and the scale, or me and the floor, right, pushing upwards to prevent me from sinking, and there's obviously my weight pulling me downwards, minus Fg. And there's no net force because I'm not accelerating, right? I'm not sinking through the floor, I'm not levitating in the air, right? And I'm not moving left to right or anything like that. And even if you were, right, it doesn't matter because we're only interested on the y-axis for now. Now, in that case, obviously, since we know that F is equal to ma, your a is 0 because you have no acceleration, you're not moving really, right? And so Fn minus Fg, and that's 0. So Fn is equal to Fg. Awesome. Now, what's going on with the whole elevator concept is that an elevator is moving. It's carrying you upwards with it, right? And so you'll have, instead of your acceleration being 0, well, your acceleration will just be whatever the acceleration of the elevator is. So let's say the elevator is accelerating at a rate of 10 meters per second squared. Well, you're also going to be accelerating at a rate of 10 meters per second squared because you and the elevator are one, basically. And so if we were looking at Fnet equations, right, Fnet equals ma, then it would be your mass times the acceleration that you're feeling because of the elevator pulling you upwards. And that in that case it would be a positive acceleration in the y direction, right? And that's still equal to, if we're looking at what's going on inside the elevator, right, if you are stepping on a scale, right, then there's a force, obviously, like I said, the contact force, the normal force, that is pushing upwards against you to prevent you from sinking through the floor of the elevator. And then there's obviously the gravity, right, pulling you downwards because of your weight. So that's the setup of our net force equation. Fn, normal force, pushing upwards to prevent you from sinking downwards, and a gravity force due to your weight pulling you downwards naturally, right? Now, the idea here is that if I were to just want to calculate what the normal force is, then I get Fn is equal to Fg plus may. So that indicates to us, in assuming that acceleration is positive here, right, because you're being pulled upward, so it's in the positive y direction, then your force of gravity added to your net force should give you, let's say for example, if this was 40 and this was 30, right? And this was 10, obviously, because 40 minus 30 is 10, right? Well, then you can see here then that this 30, this 10 will give you that 40. So what's going on here is that actually, you know what? Let me do that backwards because I think I already kind of gave the answer almost. My bad. So let's say your net force is 10 newtons, right? And your normal force is going to be that 40, right? If we were looking at or trying to figure out basically what your force of gravity is, you kind of manipulate the variables around, and you can see that that will be equal to 30. This is 10 and this is 40, right? So what you see is that your force of gravity is going to be less than your normal force. In fact, your force of gravity, your weight, plus the net force that the elevator is exerting to kind of pull you upwards, right, is going to be equal to your normal force, right? So the normal force is going to be bigger than your force of gravity. Well, why do we even care about this whole normal force concept, right? Why is that even important? Well, what you don't realize is that the normal force is pretty much what a scale gives you when you step on it, right? When you step on a scale, it's not telling you your weight necessarily, because it really can't do that in a sense. What it does is that when you step on it, you're exerting a force which is equal to your weight on the scale when you step on the scale. Now, the scale is like, okay, well, some heavy person is just stepping on me right now. And so let me try and figure out exactly how much force they're exerting, right? What's their weight? What's their force of gravity? And it's not kind of like just a kind of direct calculation. What really happens is the fact that because when you step on the scale is a solid kind of object, right? You don't go through the scale unless, I guess, well, if you're that heavy, no shame, but I mean, that doesn't happen, right? The idea is that when you step on the scale will be exerting a force equal and opposite to your weight to keep you held up like that, right? And so the scale will then project and display whatever weight, right? Or it'll display pretty much whatever force, the normal force in this case, right? That would be equal to your weight that you would be exerting on the scale, right? If that makes sense. So that's kind of what's going on when you step on a scale, right? So when you step on it, here's the scale. You step on it, here's your force of gravity, and then it projects and it gives you a value that's going to be equal to that force of gravity, Fn equal to Fg, because you don't want to sink through the scale, right? It'll just give you a value that is equal to your force of gravity, and it just so happens to be the normal force because obviously if you're exerting a weight downwards like this, the scale has to exert a specific force, normal force, between the surface of contact and you that would be equal to that to prevent you from sinking, right? And so the fact that a scale shows you your normal force, right, is where we kind of start to think about this concept of apparent weight. Because if you were to have that same scale in an elevator, right, where now there is a normal force, or there is a net force, right, because if you're just stepping on a scale on a solid surface, right, you're not in an elevator or anything, like I said, it'd be Fn minus Fg, and everything would cancel out. They'd be equal and opposite to each other because you're not levitating, you're not sinking through, so there's no net force. You're just standing statically on the scale. Now, if you were to add some kind of net force, in which case an elevator will be pulling you upwards or pulling you downwards, right, then all of a sudden, like I showed earlier, you have this F net, that's equal to MAY, where your A might be positive if the elevator is pulling you upwards. And then if you were to have that same scale inside the elevator, where the scale is showing you your normal force, right? Showing what force the scale is exerting back on you, minus Fg, which is your weight on the scale. Then you realize then that this value, the scale reading, the normal force, right, is going to be equal to not just Fg, like before, where we had no net force, but it's going to be equal to Fg plus that net force that the elevator is imparting. In which case, then your normal force is going to be greater. And so that's where we get that real life feeling of if you are moving from the first floor to the second floor to the third floor, right? If you're moving upwards, you feel a little bit heavier because that normal force that the scale is showing you, minus the FG of your actual weight, is now not just equal to 0, it's equal to some upwards acceleration, upwards net force, right? Positive here. And so in which case Fn is equal to MAY plus FG. And in that case, right, your normal force has to be greater. And so your normal force, in this case, we define that to be as your apparent weight. It's apparently what you're feeling. It's the sum of the contact forces, and the only contact force here is the normal force. So if your apparent weight is your contact force, and if your contact force is your normal force, right, then based on that equation, and based on the fact that you have a upward net force, right, a positive net force, then Fn is equal to MAY plus mg, and you can see really quickly that your normal force is greater than your force of gravity in order for you to be moving upwards in the net positive y direction, right? And so when this Fn is greater than your Fg, this is, remember, your actual weight, and this is your apparent weight. So you apparently then feel a little bit heavier. You can see that the line is even bigger here, the vector line is even bigger, to show that this is a bigger force compared to your weight. So you tend to feel a little bit heavier than you actually are. Now the opposite would kind of be the opposite would be true, right? If you were moving downwards to where F net is equal to MAY and your y is negative, right? So the whole thing is like, your AY is negative, I mean, so the whole thing would be like negative MAY, right? To give you a negative net force pointing downwards, then that same Fn minus Fg, right? Because remember, we're just thinking about this like if you were just to step on a scale, then Fn minus Fg, if we rearrange it around, we can see that Fn is equal to Fg minus MAY. So now all of a sudden, the normal force is your weight minus something, not plus something. So that would indicate that your normal force is actually a little bit less than your actual weight. So your apparent weight is a little bit less than your actual. And so what happens is if you're going down a couple floors, right, then you actually feel a little bit lighter. So the free body diagram for it would be looking like force of gravity is this big, for example, and your normal force might be a little bit less, right? In which case, you can see that the downward force is a lot stronger, and that helps or is necessary because we want to be moving downwards because the elevator is pulling us downwards. Does that make a little bit more, I guess, I don't know. Does that make sense? Or does it make more sense, I guess, if you didn't understand it during lecture? Okay, awesome. Yeah, and I kind of already went over this essentially. But yeah. And here's a really important example for this elevator problem stuff because you're pretty much guaranteed to find a problem like this on the exam. So it says Marie has a mass of 50 kilograms. She gets into a 1,000 kilogram elevator at rest, steps on a scale. As the elevator begins to move, the scale reads 600 newtons for the first 3 seconds of the ride. How far has the elevator moved and in which direction at the end of these first 3 seconds? So Marie, her mass is 50 kilograms, right? And it says that as the elevator begins to move, the scale reads 600 newtons, right? So this is 600 newtons is what the scale is reading. That's what the scale is displaying for the first 3 seconds. Now, it's also asking you how far has the elevator moved, and then in which direction, like upwards or downwards, basically, at the end of the first 3 seconds. Now, what we want to do first of all is recognize some things. So we know that the mass is 50 kilograms, right? So what would be the weight of Marie if her mass is 50? $500 newtons, exactly, right? Yep. So it's 50 times your acceleration due to gravity, so 500 newtons. For sure. Now, with that being the weight for Marie, right? If she steps on the scale and this is what it reads, remember what I said about the scale and what it projects. What is the 600 newtons? What do we refer to that as? What force is that? Exactly, should be our normal force, right? And our normal force is what? It's a what force? Remember we said it was a something blank, or just a blank force, right? So normal force is a blank type of force. Contact, excellent. Contact force, right? And the sum of all your contact forces should be what? Not necessarily just Fn minus Fg. That could be our net force equation, which is excellent. But the sum of the contact forces, remember, Fn is our only contact force, right? Fn is the only contact force that we have here. It's between an object and the surface of contact, right? So if Fn is our only contact force, if you remember, the sum of all the contact forces should be our apparent weight, right? So this essentially is our apparent weight, or FAP, right? But yeah, that's our normal force, so excellent. So really, in the end, they're not actually asking you really about any force values, right? Not even like the net force or anything like that. What they want you to do in the end is figure out the distance that the elevator is moved after 3 seconds, right? Well, how can we figure that out? Remember when we're talking about stuff like distance, displacement, velocity, all of that stuff, right? We might need some of those types of values, right? So we don't know what delta x is. That's what we're trying to figure out. That's how far the elevator is moved after 3 seconds. Well, 3 seconds, t is 3 seconds, right? So there's our t, right? Now, the issue is we don't have values like maybe velocity or acceleration, right? Could we get any of these two values? Could we get velocity and acceleration? Yeah, right? So let's kind of think about, go back and look at what kind of information we have access to. So we know that her mass is 50 kilograms, so her weight is 500 newtons, and then her normal force or apparent weight is 600 newtons as well, right? So if we were to write a net force equation, Fn minus Fg is equal to may, right? Then we can see that the 600 newtons is our normal force. Here's the 500 newtons for your gravity or weight, and that gives us 100 newtons as the net force, right? And we know then the acceleration has to be positive, right? Because, at least from a conceptual standpoint, right? Because if we know that she feels heavier than she actually is, then we could say that she's been moving upwards, right? Based on that kind of feeling and that general concept that we were looking at from before, right? But maybe we don't want to jump too ahead of ourselves, and let's kind of slow down a little bit, right? And take it one step at a time. Now, if we have may is equal to 100 newtons, right? Well, if her mass is 50 kilograms, right? We know that. We know Marie's mass is 50 kilograms. If we divide 50 over, we can get her acceleration that she's feeling, and that's 2 meters per second squared. So that's an acceleration that's positive. Okay, awesome. So that positive acceleration automatically then confirms what we know conceptually, and that is the fact that the elevator is moving upwards now, right? So positive acceleration means it's moving upwards. Negative acceleration means it's moving downwards. So we have this acceleration now, right? So that's awesome. Now, we want to figure out how far the elevator's moved upwards after 3 seconds, right? So we can start to use or think about maybe some kinematic equations that we know, right? So we know that we have VF is equal to VI plus AT, right? That could be a possible equation that we could use, right? And the reason why we can use this is that, well, if we're trying to figure out how far it's moved, right, the delta x, then, or well, in this case, it wouldn't be delta x, it would be delta y because it's along the y-axis, right? But the idea here is that we're trying to get to this delta y somehow. Well, we can figure out this delta y if we know some sense of what the final velocity was after those 3 seconds and what the initial was, right? So we could use this equation, but we don't know what her final velocity was, right? We don't know after 3 seconds how fast she's moving or how fast the elevator is moving, right? But we do know that the elevator starts at rest. Whenever something starts at rest, then you know that your initial velocity has to be 0 meters per second, right? So if we can use that, you can use this equation. We know that 3 seconds has elapsed. We know that we're accelerating at a rate of 2 meters per second squared, and our initial velocity is 0. So that helps us figure out our final velocity of 6 meters per second, right? Now, that's our final velocity, our initial, and then 2a delta y. So we know that our initial was 0 from before, right? And we know our final was 6 meters per second. So if we square that, that's 36. And our acceleration from before was 2. So you can solve for that and figure out that, your delta y, right, should be 9 meters. So in that case, the elevator has moved 9 meters upwards based on this acceleration value that we got from the net force equation. She's moving upwards at a rate of 2 meters per second squared. She was initially at rest, and after those 3 seconds, she's moving at a speed of 6 meters per second. Does that make sense? How to relate like this net force like stuff to maybe some kinematics concepts from like week 1, week 2? Okay, awesome. Yeah, there's like an example for here as well. Another quick check as well here is like if you have 50 kilogram student, so their weight obviously would be 500 newtons if we multiply by the force of gravity, or the acceleration due to gravity, and they get into a 1,000 kilogram elevator at rest, and then that student hangs on a rope attached to the elevator ceiling. As the elevator accelerates downwards, what is the student's apparent weight? Right? What is the student's apparent weight here? Well, if they're hanging onto the rope, right, then what do I want to say here? Actually, I'm not sure if this is quite right here. I mean, essentially, we're going to use the same method of thinking right here, right? Similar to the normal force stuff that we were doing before, right? Then we should have Ft, the tension force due to the rope, kind of pointing upwards, right? Because if she's hanging from the rope, that's what's going to be pulling her upwards, essentially. And then minus Fg, which is the weight, right? Her force of gravity pulling her downwards. And then we know that if the elevator is moving downwards, then it should be a negative net force, so negative MAY, right? And don't put like a double negative here, because you know that your acceleration is going to be negative, so your overall net force is negative. So I wouldn't do like negative negative m, right, times negative AY. Just know that since the acceleration is negative, like if you had mass times a negative acceleration because you're moving downwards, then we can essentially just pull out this negative just to clean things up. So yeah, just don't make a double negative mistake there. But it'll be Ft is equal to Fg minus MAY, right? And that would be kind of the setup there for your force of tension. The only thing is that I'm not sure about, I think I might have made a mistake on this slide, is that I wouldn't really define tension as a contact force. But I suppose if obviously the student is in contact obviously, right, with the rope, then in that case, that tension force would be representing her apparent weight. And so, like, what I'm trying to think about is like, okay, well, if we were to think about this, sometimes I obviously kind of have to think about things maybe in like a more real life context, think about what would happen in real life. So if I were to just hang from a ceiling, right, in an elevator, theoretically, then if I'm moving upwards, right, um, then my equation would be set up in the sense that ft minus fg is equal to positive may. And in that case, fg plus may is equal to tension. And so I guess if you're moving upwards like that, the rope might feel a little bit more tense, quote unquote, or it might be stretched like a little bit more taut or tight, right? And if you're moving downwards, it might be like a little bit more loose, essentially. And so I guess in that case, right, if your actual weight is 500 newtons and your force of tension is equal to your actual weight minus that net force downwards, then your apparent weight should be less than 500 in that case, but not necessarily zero, obviously, right? Yeah. I think if you weren't to define tension force as a contact force, right, then you could say D if there isn't any normal force, obviously, in this case, but I will double check this just to make sure. I think this might be a mistake, but I'm not 100%. But I will let you guys know about this. I can reach out to you guys later about this, but I think this is correct as of now. Let me actually look it up just real quick, just to double check. Yeah, I guess. Yeah, that's fine. Yeah, we can consider tension force here to be a contact force because you're directly in contact with the rope. The rope more or less is kind of like your surface of contact there. Because like I said, you can think about if you were leaning on a wall, then it's between your hand and the wall, and your wall is the surface of contact. But now you're hanging on a rope, so you're just hanging. It's the surface between your hand and the rope, essentially. So yeah, this one's good. If you're weightless, you have no apparent weight. That's kind of just a one-off, concept there. And if you're in free fall as well, you have zero apparent weight because you don't have any contact forces in free fall. You're not in contact with any specific force. So you feel weightless. Now we're getting to the friction stuff, right? And I kind of went over this earlier, but like I said, kinetic friction is going to be basically the frictional force that is going to be acting against an object that is already sliding, right? And we denote that as Fk, F sub k right there, right? And it's always parallel to the surface that you're sliding on or moving on or whatever, right? Now, obviously, like I said, friction, just think about that as a force that opposes another force, essentially, right? So for kinetic friction, if you're trying to slide to the right, then the kinetic friction would be opposing that sliding to the left. Now, static friction is a frictional force, right, that will keep an object from slipping or sliding. It keeps it stuck, right, preventing motion at all from happening, right? So think about, like I said, for static friction, it prevents that slipping and sliding and prevents anything from happening. It's a cautious force, let's say that, or it's a preventative force. Now, kinetic friction is like, all right, well, might as well, like, it's happening now, so let's try our best to stop it, right? So you're already sliding, and so your kinetic friction will try and alleviate that and, try to stop whatever sliding is occurring. Static friction will try to prevent that sliding from occurring at all. Rolling friction, like I said, is not going to be as frequent. of a concept, very similar to kinetic friction, but it's for objects that roll, like wheels, tires, like that, instead of sliding. But really, rolling friction isn't as used or as frequent of a concept. So I would just focus on static friction and kinetic friction. Like I said, static friction will keep things static, not moving, right? Just to keep them stationary. Think S static, stationary S, right? And your kinetic friction will try to prevent things from moving, right? So if you think about like kinetic energy, if you've heard that in a science class, right? Kinetic as in motion, right? So it'll try to prevent whatever motion is occurring. Kinetic friction, that's the equation for it. It's mu, right? That's your little coefficient of friction there, times your normal force. And it's equal to this for sure. Like kinetic friction is equal to mu times Fn, where mu is the coefficient of friction, and this is unique to every surface, right? And your normal force, we already defined that as well before. I'm going to skip an example here because this isn't too bad for kinetic friction. Rolling friction, similar kind of setup where you'll have coefficient of friction, coefficient of rolling friction, right? Times your normal force, same kind of deal. But it'll be with wheels and tires and stuff like that. Like I said, it's not as used. Static friction is a little bit weird because really it's a variable force. It can increase itself to a maximum point, basically, right? So something just sitting there without exerting any forces will have a static friction of 0. If that object isn't exerting any force or nothing is acting on that object completely, then there's 0 static friction force, because at that point, if nothing's acting on it, on the object, right, or if the object isn't acting on anything, then there's no point to stop it because it's not doing anything. So what's there to stop, you know? But with the idea of this static friction force being a variable force, the idea is that if there's something to stop, the static friction force will adjust itself to stop it, right? So if you're only exerting maybe like a 10 Newton force, then the static friction force will adjust itself, increase itself to a 10 Newton force to stop it, right? If you're exerting 100 Newtons, it'll jump up to that 100 Newtons to prevent any motion. In that case, like I can use that example again of the car on a hill, right? If you're parked on a hill, you have force of gravity, right? You'll have an X component to that force of gravity trying to bring the car sliding down the hill, right? And so in this case, that force, the X component of force of gravity, is constantly acting to try and pull the car down the hill. And so static friction force will try and prevent that, pointing to the right, essentially, right? Now, let's say someone might like be pushing on the car downhill as well, or maybe there's some ice, right, that will essentially kind of make it more prone to slipping. So in that case, you might have an ever increasing force, right, trying to pull you down the hill. There's a point where it's like, all right, static friction force can no longer handle whatever force is trying to bring the car down, right? The force is too strong, right? And so the static friction force will keep trying to adjust itself as big as it needs to be to keep an object from slipping. But there comes a point where it's like, okay, there's too much force now that's acting. It's inevitable that it's going to slide and slip, right? And that's the maximum magnitude of the friction force, the static friction force, right? So here, if a woman is pushing on a box, right, that box might be super heavy, right? So to prevent the box from actually moving, right, to prevent anything from happening, there's a static friction force. Say if you pushed with 100 Newtons, static friction force between the surface, right, between the floor and the object, between the floor and the block, right, or the box, will be 100 Newtons to the left, negative 100 Newtons, right? You might continue to push harder, maybe double that force, now 200 Newtons, and that static friction force will adjust itself to double itself as well to prevent the object or the block from moving. But then you might kind of exhaust the static friction force, right? To the point that now, okay, I'm like, all right, well, now let me just push even harder. Let me really push it to 500 newtons. Well, maybe the maximum static friction force that can occur between the surface and the block, it could only be 400 newtons, for example, to the left. Well, now you've overwhelmed it, and that's what happens when you're actually able to move an object, right? So you might push harder and harder and harder in something until it actually starts moving. When it actually starts moving, you've essentially just exhausted the static friction. You've overcome it. You overcame it. You're right. You've overwhelmed it, is what I meant. So the point where that occurs, where the maximum static friction occurs, is when you have mu times Fn, which is coefficient of static friction times your normal force, right? And that's very similar to your kinetic friction. The only thing is that this less than or equal to sign accounts for the fact that it's a variable force. So static friction force can be anything less than that maximum, right? We could have it where there's absolutely no static friction force whatsoever, zero, if there's nothing acting on the object, right? Or it can steadily increase the more you push on it, the more you act on an object, up to when it's equal to the coefficient of friction times the normal force of the object itself, right? So that means it could be 0, it could be 100, it could be 200, or it could be the very maximum equal, right, to this, right? So you can't just say static friction force is equal to mu times Fn and calculate for it, right? You can't do that. There'll be trick problems on the exams and the quizzes that will make it seem like you can do that, but really, it's a variable force, right? Unless you know that the object is about to slip. If they say the object is about to slip, then you know that static friction force is pretty much exhausted at this point and is going to be equal to mu times Fn. Otherwise, it could be anything less than. It could be, if the maximum is 500, you don't know if it's going to be 499 or if it's going to be 200 or if it's going to be 0, right? It just depends on what force is acting on the object and trying to make it slip. But that's the idea of static friction force there. Make sense so far? And it adjusts to the force you exert up to a specific maximum value equal to mu times Fn. All right, awesome. Yeah, and this is kind of a reiteration of that. If the box isn't moving when you pull on it, then you know that your static friction force is going to be equal to the tension because it's going to try and cancel each other out, right? To prevent any slipping or sliding, to prevent any motion, right? Let's see here. So, I don't know if we should do this example real quick or not. I'll try and come back later to it if we have some time, but we're kind of running low on time at the moment. This is going to be some examples here as well with respect to friction on slopes, right? And really it's going to be the same concepts. It's just that now instead of having a flat horizontal surface, everything's going to be on the tilted axis here with the inclined plane. So let me see if these are just example problems afterwards. I think they are, with exception to Newton's third law. Yeah, I want to make sure I get to this third law stuff because that's what's a little bit confusing. Look at that real quick. And then I believe, if I'm not mistaken, let me check real quick. Since we're kind of running low on time, and that's just kind of partly due to the fact that we just started a little bit late, had some technical issues at the beginning. Let me double check. I believe I have a video on this. Like I fully went through this lecture last semester, I believe. So let me double check and make sure that was the case. Let's see here. Yeah, yep. I went over this lecture. Let me actually play the video real quick. Make sure that I did. And I think now that I've Yeah, it's on my YouTube channel, yeah. I have like videos for all of last semester and everything on the YouTube channel, so you guys can always refer back to that if you need help with the homework, um, if you need help understanding concepts and stuff, all of that. Yeah, I went over the lecture slides, yep, and in detail as well in the video from last semester. So let me drop that in the chat there so you guys can have that. That's the direct link to the video there. So what I'll do is probably kind of stop going over things for the moment, because I know I went over like practice problems from the quiz from last semester as well. So what I'll do is I'll kind of stop it for now and leave these last couple of minutes kind of as an open like question kind of thing, where you guys should just throw some questions at me and see if you have anything specific you want to focus on, anything in particular that you're not quite understanding, and I can address that, because the rest of this lecture pretty much, and I have some quiz problems, those are already on the YouTube video that I shared. So I mean, and I went very in depth with those anyway, so I just want to make sure that I'm addressing maybe like the most important things to you guys. So I'll just kind of leave it up for questions now, I guess. Sorry if it seems like I'm ending it kind of abruptly. It's just that, like, I know I did like the full job last semester for sure, and since I started late tonight, I just want to make sure that I'm addressing as much as I can. And if I already did something last semester, like, I guess there's not a point to kind of repeat it, because I know I did it well last semester. But yeah. Do you guys have anything specific that you want to focus on? Feel free to unmute as well, and we can just talk about this stuff casually, right? You're good? Yeah, I mean, if there's nothing else you want to talk about necessarily, if there's no other specific examples you want to go over, yeah, if you want to just go ahead and watch the video as well, that's totally fine. I would recommend really watching out for these types of problems. These like block problems, when they're stuck to each other, like this, are very, very important. It's a guarantee that you're going to have a problem like this on the exam. It came up on my exam, came up on the exam after my semester when I was tutoring for physics, came up on the semester after and the semester after that, right? I've been tutoring for physics for like 3-4 semesters now, and it's come up every year. So definitely focus on these types of problems right here. Especially there's an example where it's like a block is actually on top of another block. There's a group problem on this, I believe, and there's also practice exam problems on this, and I will be sharing some practice exams for your exam review next week. But the idea with these is that when you're drawing your free body diagram for this, you want to draw it in a way, and you address forces in a way to show what each object is feeling, right? So if I look at A and B right here, A is feeling a force of gravity, right, due to the Earth. It's feeling a normal force due to the surface that it's sliding on, right? And then additionally, it's feeling a force from B on itself, on A, right? That's what it's feeling. B, on the other hand, right, if we're pushing B onto A, if we're pushing to the right or to the left like this, right, B is feeling a normal force, or a force of gravity, right, downwards due to the Earth. It's feeling a normal force due to the surface of contact. And then if we had a hand here or something, right, pushing the block, we feel that hand, right, that block feels a hand on itself, on B. And then the fact that block B is being pushed into A, B also feels kind of a normal force, a contact force, right? It's coming into contact with A. So B feels a force from A on itself. So the way I kind of explained it last semester was like, if you um, thought about this is I don't know if it's intuitive, if it's not, I don't know, but like it seemed to kind of help students understand last semester. But the idea is that if you're standing in a line, right? Let's say here are three people, right? This person, this person, this person, this person, right? This person right here, person number 1, 2, 3. Number 1 might push number 2, right? Number 1 pushes number 2. What does number 2 feel? Let's think about this as the hand. This is block B and this is block A, right? This person number 2 feels the fact that person number 1 pushed them, right? Person B or person 2 right here fell over, right? They fell over. When they fall over, they also unintentionally push A, right? Well, when A looks back and is like, all right, well, who pushed me, right? Who are they gonna blame? Who are they gonna immediately look for? They're immediately gonna look for person number 2. They're like, oh, you pushed me. Well, that wasn't necessarily the case. It was actually person 1. But person 2 has no, idea of that. They have no way of knowing that it was actually a person behind person 2 that pushed them and caused everything to topple over, right? So person number 3 or person A right here, when we draw a free body diagram for them, we're trying to draw things in terms of what each person or what each block feels. Block A, person 3 is only aware of the fact that person 2 or person B bumped into them, right? Person B, on the other hand, is kind of like getting sandwiched. Not only do they feel and they know that person 1 pushed them, but then they got smushed into person 3, right? And so that's why when we draw this block B, they feel person 1, right? They feel that hand on block, right? And then they also feel the fact that they got pushed into this person. Let's say if person 3 was Dwayne The Rock Johnson, right? That man is not falling over. No way. So it's basically just a brick wall in front of them. So if they're getting pushed by person 1, then they also feel the brick wall that is Dwayne The Rock Johnson in front of them, right? So they have to feel this force of A acting on that block, B, and they also have to feel the fact that the hand, pushed them on block B, right? And then obviously your normal force and gravity force are common, right? There's no issue with those. But it's the normal forces that kind of throw things off between the blocks, like between the surfaces. So the fact that B feels itself getting smushed into A is the force right here that kind of throws people off. And I personally got a whole 2 parts on the exam incorrect just because I didn't really understand this part right here. But does that kind of clear things up as to how you should draw the free body diagrams? Does the people in the line thing make sense? I just use that analogy and I hope it kind of sort of cleared things up. But yeah, I think that's also a very, very, very important concept to understand. Yeah, and absolutely, there's going to be friction here as well. And the friction would just be between, for either one, right? If they're sliding, right, then it should just be kinetic friction opposing them both, right? Each one was going to be feeling a kinetic friction. Now, with that being said, that is an excellent, I can't even tell you how good of a question that is, because on my exam, we had a block on top of another block. It was a really big block and then a smaller block on top. The big block was being pushed essentially, and it was feeling kinetic friction because it was sliding, right? We already talked about how kinetic friction is for sliding. Now, the smaller block isn't necessarily sliding, but it's also feeling friction. What type of friction do you think it's feeling? Because think about it, there's potential for that block to slide, but what could be preventing it from sliding? Excellent. Static frictions. You're already better than I am at this point because I just overlooked that on the exam. And so static friction, like we said, it's a preventative force. It's a cautious force. It's going to prevent something happening before it happens, right? So there's potential maybe for that block to slide off of that smaller block to slide off of that bigger block, but static friction force is keeping it in that position, keeping it from slipping and sliding. On the other hand, if you're really pushing this big block and you're sliding already, well, then the kinetic friction force we kind of talked about is like, all right, well, what do? It's sliding. We can try to stop it. We can try our best, but it's sliding anyway, right? So static friction is kind of a preventative, a cautious force that tries to prevent something from happening. And then kinetic friction, well, we're sliding now, so might as well try and, dial it down or, dial it back a little bit. So kinetic friction force will try and prevent that sliding. But yeah, strongly recommend kind of going over this again. And like I said, I have the video from last year, and I use the same examples, same analogies as well. I think I just had a little bit more time to explain it last semester since we started a little bit late tonight. And I explained Newton's third law as well, and I've kind of gone over that a little bit in the beginning of the presentation, in the sense that for normal force, right, if you are standing on a floor, right, you'll have certain gravity, certain weight, and then basically with that certain weight, you'll have a normal force that will be acting opposite but equal magnitude to that weight in order to prevent you from sinking through the floor, basically. Right? So, equal and opposite. Every action, there's an equal and opposite reaction. Right? So, force on A on B is the opposite of B on A. Different direction, just same magnitude. That's pretty much it. This slide is like super important. I wish I had more time to kind of go over it. But like I said, I thoroughly explained all this stuff last semester. So if you want to check out the video as well to kind of go over this stuff again, I think that would be a great option. And then, like I said, I'm always open for questions. Feel free to DM me here on Discord. Send me an email. That's totally fine. Anything like that, more than happy to help. And like I said, I will also post my lecture slides on the Google Drive. So before you guys leave real quick, let me share the Google Drive, and after the session I will just go ahead and upload things. I'll upload this recorded session to YouTube as well. But yeah, so 1 second here. I'm just let's see here. Okay, additional resources. All right, so here's the link. I believe it's under week 5, actually. At least for our semester, it was week 5. So let me just drop the link here real quick. So there's the link for the... Actually, you know what? Before I do that... Okay. Let me actually adjust some things around. 1 second. Sorry about that. Okay. Let me just say this is week 4. Boom. Okay.